So let's do one more steady state temperature. Just like before, the PDE comes from assuming that the temperature depends on the radius and on Z. So the PDE is the same as the one before. So I'm not going to do, again, the separation of variables. I'm just going to focus on solving the Sturmoville problem in basically the rest of the solution. So the work of separation of the equation is the same as before. This time we have a finite or closed object. So a cylinder with a defined top and bottom. And again, to make it easy, let's say the radius is 1 of the cylinder and the height is 1 as well. So Z is between 0 and 1. Let's see how we look at the boundary conditions. Let's label these conditions 1, 2, 3. So the exterior is kept at 0. The exterior, I mean the surrounding, the exterior side, not the top and the bottom. Pause for a moment and actually try to write these boundary conditions yourself. It's very important actually to do that. So don't try to, cheat yourself basically when doing that. Just pause, take a couple of minutes, 5-10 minutes if you want to, and really try to write the boundary conditions in terms of conditions on U before you check with me. All right, so assuming you just did that, let's check. Okay, so the exterior is kept at 0. Exterior is identified by the radius 1. Okay, so a way to write this down is to say U of 1Z equals 0. So along the cylinder, but on the exterior, when the radius is 1, I want the temperature to be 0. Second condition, the bottom is insulated. Insulation means no heat transfer with respect to the space gradient, right? So that means in the direction of Z, right? Because again, the bottom is basically described by Z equals 0. So across the bottom, right, from up down, I mean in the vertical direction, there's no heat transfer. So the partial derivative with respect to Z at any point on the bottom, which means the radius can vary, rho, but Z is 0. Again, Z equals 0 identifies the bottom of the object, is equal to 0. So insulation, as you remember, that leads to Newman type of conditions, basically. Moving on, the top is kept at 1 degree. This will be our non-homogeneous condition, which we will deal with at the end, right? So U of rho 1, again, the radius varies, but Z equals 1 identifies the top of the cylinder. So U of rho 1 equals 1. So these are the boundary conditions. And let's see how they look like when we use separation of variables. So remember, U of rho Z is assumed to be a function in rho times a function in little z. And so the boundary conditions now, if I plug in this format, become R of 1 big Z of little z equals 0, which implies R of 1 equals 0. Second condition means R prime of rho, because it's, excuse me, sorry about that. R of rho Z prime of 0, because you do partial Z, right? So it's Z prime of Z evaluated at 0 equals 0. This implies Z prime of 0 equals 0. And finally, this one, you leave it at that because you're going to deal with at the end after the superposition principle. So, because it's non-homogeneous condition. So the Sturmoville problem, again, will be a Bessel equation of order 0. So assuming the separating constant by even given by minus alpha squared. Just like before, if you want to take a look at the previous part, you can do it, but you're going to arrive to this equation in R, and the relevant boundary condition is R of 1 equals 0. And let's write side by side the equation in Z, just like before, will be Z double prime minus alpha squared big Z equals 0 with another boundary condition. Last time, remember, there was no other condition on Z except the boundedness condition, but now we have another condition, Z prime of 0 equals 0. Remember, this will be solved for each eigenvalue and eigenfunction from the Sturm-Liouville problem. All right, so what do we know about Bessel function of order 0? The solution of each of them is a Bessel function of order 0, because C is equal to 1, then the solution will be J naught of alpha rho. So J naught of alpha rho is the solution of this equation. R of 1 equals 0 implies J naught of alpha equals 0. This is the moment to stop and look at the boundary conditions listed in those Fourier Bessel series. So then anticipate that you're going to have to use formula A in that handout when the time comes to actually come up with Fourier Bessel series. At this moment, just state that this equation, J naught of alpha equals 0, has the roots alpha 1, alpha 2, and so on, alpha j and so on, right? I mean, infinitely many positive roots. So alpha j's are the roots of this equation, just like before, or I mean, not just like before, similar to other problems, because in the previous example, remember, there was a different boundary condition from the Newton's law of cooling. So going back now to the equation in Z, we solve that for every alpha j. So we're going to have Z double prime minus alpha j squared big Z equals 0. The solution will be, and we can label it now, big Zj of little z, is going to be some constant Aj e to the alpha j little z plus Bj e to the minus alpha j little z. Make sure you pause so you can follow through. Because look carefully, now we have to apply the boundary condition, I mean the condition that we have here for the equation in Z, which is in terms of a derivative. So I need to differentiate big Z first, and then plug in 0. So pay attention how there is this minus alpha j coming up here from the chain rule. Now we plug in 0 and set it equal to 0. And the condition becomes alpha j big Aj minus alpha j bj equals 0. We can pull out alpha j, and that means Aj equals to Bj. So the condition Z prime of 0 equals 0 simply leads to the conclusion that Aj is equal to Bj. So now again, let's wrap this up right before the superposition principle. Again, it's very important to understand this step, which is essentially the same in all of these problems, but it has to be very clear in your mind, right? What are the eigenfunctions? Well, the eigenfunctions are, again, you can at this point label them by J, right? Because you have infinitely many alphas, right? So the eigenfunctions Rj of rho are nothing but J naught of alpha j rho. Alpha j's come from the eigenvalues, right? The roots of this equation. Rj, J naught of alpha j rho is your eigenfunction. For each Rj, you just found a solution for the Z equation, which again, if Aj is equal to Bj, going all the way back over here, you can replace Bj with Aj and factor out. So Zj is e to the alpha j little z plus e to the minus alpha j little z. In the book, sometimes you don't have to do it, but in the book, sometimes this is given by AJ cosine hyperbolic of alpha jz. Because if you divide by 2 and you put that extra 2 in the constant AJ, this over 2 is just the cosine hyperbolic, but that's optional, so you don't have to bother with that too much. Okay, so we're going to have superposition principle between these two, and let's move on to another page to finish the problem. So with the superposition principle, my solution u of rho is little z is a series from 1 to infinity. I'm going to start with zj first. So aj e to the alpha jz e to the minus alpha jz times the Bessel function, which is j naught of alpha j rho. So remember, the other condition to deal with, the very last one, was the non-homogeneous one, u of rho 1 equals 1. So now we're going to plug in 1 for z. So we're going to state what u of rho 1 equals 1 means. So this leads to the summation from 1 to infinity, aj e to the alpha j times 1 plus e to the minus alpha j times 1 j naught of alpha j rho. This should be equal to 1. So we met this type of situation before. Notice that aj are not going to be by themselves the Fourier coefficients. Aj together with this parenthesis will be the Fourier coefficient of 1. So now we have to write 1 in terms of a Fourier. You have to basically write 1 as a Fourier Bessel series in terms of these Bessel functions. So once again, this entire quantity will be the Fourier coefficient. So if you look at the formula sheet, this should be equal to the Fourier Bessel coefficient. For the function 1. In the formula sheet, you have f of x equals 1. Here, my x is replaced by rho. Not a big deal. Okay, so now what is the actual condition for that? Let's see. I misplaced the formula sheet. Yeah, just a second. All right, so the formula A in my case will be 2 over c squared, which is 1, c is 1, so it's going to be 2 over j1 of alpha jc, c is equal to 1, so 2 over j1 of alpha j to the power 2, and then the integral from 0 to 1, because again c is 1, rho instead of x, the function is 1 again, and j naught of alpha j rho d rho. All right, and again, just like before, this can be computed, but let's do it a little bit faster now. Remember, our starting point is always that change of variables. So let's continue. New bounds of integrations are 0 and alpha j. Rho is replaced by s over alpha j. This is j naught of s now. D rho is ds over alpha j. So on the outside, we have 2 over alpha j squared, j1 of alpha j to the power 2. And remember, what's inside the integral can be written as the derivative of s j1 of s. And when I plug in alpha j and 0, really the same integral like before, okay? It's going to be alpha j times j1 of alpha j. Okay. And let's see. We have some simplification. Alpha j cancels with this, j1 with this. So you're left with 2 over alpha j, j1 of alpha j. Remember, this is not aj, right? Again, this is going to be the whole coefficient of j naught of alpha j rho in the solution itself. The actual aj, which comes in the end in the solution, is going to be 2 over this divided further by this. So it's going to be 2 over alpha j, j1 of alpha j, e to the alpha j plus e to the minus alpha j. And you have actually similar problems in the homework, right? And if you plug it back into the full solution to the problem, u of rho z would be the summation of aj. So let's copy this part here. So 2 alpha j, j1 of alpha j, e to the alpha jz plus e to the minus alpha jz, e to the alpha j plus e to the minus alpha j, and then j naught of alpha j times rho. So that's why in the back of the book sometimes you have solutions of these problems given in terms of cosine hyperbolic of this over cosine hyperbolic of this. So another alternative, you'll see this quantity here replaced by cosine hyperbolic of alpha jz over cosine hyperbolic of alpha j. That's optional, not a big deal, just to make it more compact. So let's leave it at that for now. Again, I want to emphasize one more time that unless you actually go over this computation yourself, to the point where actually start with the problem all over again without looking at the video and see if you can follow through with all the steps until that happens to you. So until you can actually close the video, and with the resources you have, the formula sheet, because it's open books and notes, remember? So with all the resources you have, if you can do the problem from top to finish and you understand every single step, then that means you're sufficiently prepared. If not, that's not going to work. So I want to be very clear on this from the beginning. You must go through all these computations as if you're actually grading me. So I mean, basically you need to check every single step to make sense. So that's it for today. I think this is going to be basically the last example. Maybe I'm going to add another video with comments, or let's say final comments on the Bessel functions. Not necessarily with full problems, but just comments here and there. But other than that, I think that's going to be the last part on the Bessel functions in terms of the theoretical part. I mean, the lecture part of the course. So that's it for today. I'll see you next time.